So, some examples of finding residues. So, this, by the way, is not particularly standard notation, but it seems fairly obvious what we mean. So, we've got residue of a function, and we want to find the residue at this singularity located at IA. Okay, so this function here, what we basically need to do each time is work out whether it's a simple pole or not. So this is a simple pole because we can factor this. You can factor it into z plus IA times z minus IA. If you got something like z plus IA or z minus IA, those are both have simple zeros. So therefore, when you got 1 over, they're simple poles. So simple pole method. The one I always recommend is p divided by q dash. So p is 1, q is z squared plus a squared. So q dashed is 2z. So just the answer then is just 1 over 2z evaluated at z equals ia. So that's just 1 over 2 ia. Now this one is very similar to the most, well, obviously this one is, if this is a simple pole, you've got the same thing but all squared. It's going to be a double pole, or pole of order 2. This is where I would recommend using this differentiation method, the multiple pole differentiation method, if you're asked to find the residue. So what we do is we take this result here and we differentiate with respect to A, both sides. So we differentiate this with respect to A, and we get 2A, we actually get minus 2A on top, and divided by z squared plus a squared squared on the bottom. That minus 2A we can move to underneath here, and that will give us, and then we need to differentiate this as well. So differentiating this gives us minus 1 over 2ia squared, differentiating with respect to a, and then when we move the minus 2a over here, we end up with the minus signs cancel, we end up with an negative factor of 2, a negative factor of a, so we finally end up with this. Okay, next one. So what do we have here? We always need to check top and bottom. So when z equals I pi, the top is not 0. So we're fine. Obviously, when z equals I pi, the bottom is 0. This is just a simple pole. So p is e to the az. I'm going to substitute in the I pi into the z bit there immediately. So I've got e to the I a pi. Then the bottom bit, I differentiate that. It's q dashed I want, that gives me e to the z, just e to the z. And e to the z, when I substitute I pi, gives me minus 1. So that's where the minus comes from. So very quick. And last one, what do we have here? Well, cos pi by 6 is not 0. In fact, it is... okay, come back to that. When this is p, this is q. Q dashed is minus 2 cos z. So we end up with cos z divided by minus 2 cos z. So that's easy to evaluate. The cos z's cancel, and we just end up with minus 1/2. Okay, so question 17, you go back to question 15 and find the residues for any 2, not all of them, just pick 2 of the singularities for each part. So you've got 5 parts, A, B, C, D, E. Pick any 2 of the singularities and find the residues for them. So if you're familiar with Mathematica, then residues are easy to find. Just use this formula. So this will give you the residue of the function f at z equals z0. If there's no singularity, or if it's a removal of singularity, you get the answer 0. But anyway, this is what you would enter to check this particular example.